Patterns and inductive reasoning. First, let's just define a few terms. A conjecture is an unproven statement that is based on observations. Inductive reasoning is the process of looking for patterns and making conjectures. And a counterexample is an example that shows a conjecture is false. So now let's use that inductive reasoning to study what pattern we have and predict what the next figure or number is going to be. So in this first one we have 1 dot, 3 dot, and then 6. But as you can see, they're arranged in a certain pattern, so we want to try to find that. We have this one singular dot and it shows up at the top of the next two. In the second one we added a row underneath of 2 dots, and that one shows up here in the middle. In the third one, we added a bottom row of 3 dots. So if we were to continue this, first we would have to draw the figure that we have previously, so the 6 dots that we already have, and then we would want to add a row of 1 more across the bottom so that we have 4. And then the next one we would add a row of 5 at the bottom. Now, in this next set, we see a triangle, a square, and a pentagon. So your very next thought is that the next should be 6 sides, a hexagon, and that's right. But not only are we just increasing the sides of the polygon by 1, but as you can see, we're also connecting the vertices inside of the polygon. So from our hexagon, we want to make sure we connect all of the vertices that are inside, one at a time, until we get all of them. So this is our next figure. Now the last two examples that we have are number-based. So we want to look at the pattern again and try to predict what the next number will be. So we have 1 over 2, 2 over 3, 3 over 4. So if you notice, the denominator becomes the numerator of the next number, and then we add 1 to get our new denominator. It moves to the numerator, add 1. So our next number is going to be 4 in the numerator, and then we'll add 1 to get 5 in the denominator. Now this last example, we go from 27 to 9 to 3. So we're getting smaller. So in order to get smaller, we're either going to be subtracting or dividing. So you want to think carefully. You want to find a consistent pattern. We're not going to find a consistent pattern subtracting. So let's try dividing. 27 divided by 3 gives us 9. 9 divided by 3 gives us 3. So 3 divided by 3 will give us 1. Here we just want to work on finding a counterexample. Now remember, a counterexample is an example that proves the conjecture to be false. So we want to find an example that proves these conjectures false. The first one says that the sum of 2 numbers is always greater than the larger number. So first I want to show you an example of this that proves it true, which would be that 1 plus 3 equals 4. Now, this is saying that when you add 2 numbers, that answer is going to be bigger than the larger of the 2 numbers that you added. So 4 is always bigger than 3, right? So this is an example, but we want a counterexample, something that proves this false. So I'm going to bring in some negative numbers, okay? If we take 1 plus negative 3, that gives us an answer of negative 2. So negative 2 is our answer, but between the 2 numbers we added, 1 is the bigger one. Is negative 2 bigger than 1? That's our question. And the answer to that obviously is no, it's not. So here is our counterexample. Okay? So I just wanted to show you the difference. Now let's go through and try these next two. If the product of 2 numbers is even, then the two numbers must be even. So this is saying, remember, product is multiplication. So if we're taking two numbers and we're going to multiply them together and you get an even number, then that means both of these numbers have to be even. Is that always true? I want you to try to pause and then think about whether you can find a counterexample so that you have two numbers that are not both even, but you get an even answer. And when you have that, check back with me and see how you did. Were you able to find one? Hopefully, you probably tried to multiply an odd number times an odd number, and you should have tried an odd number times an even number. Now, an odd number times an odd number will always give you an odd number. But if you multiply an odd number times an even number, you will get an even number. So, just as an example, 5 times 6 is equal to 30, which is even. So as long as you came up with a set of numbers that are one odd and one even, and when you multiply them, you should get an even answer. Let's look at this last one. It says the square root of a number x is always less than x. So the idea, again, an example, when you take a square root, the square root of 4 is equal to 2, right? So it's saying that this answer 2 is always smaller than the number you took the square root of. Okay? So again, this is an example, but we want a counterexample to prove it false. So I want you to go ahead and pause, try to see if you can find a counterexample on your own, and check back with me when you finish. Were you able to find one that works? I know this one's a little tricky. So good job if you did find one. If you didn't, let's talk through it. So let's look at the square root of 1/4. When I want the square root of 1/4, that means I'm actually looking for two different numbers that when you multiply them, they equal 1/4. So two numbers multiplied by exactly itself to get 1/4, 1/2 times 1/2. Now, which is bigger, 1/2 or 1/4? We know that 1/2, like if I gave you half of a cake, that's definitely bigger than 1/4. So the way that you'll find a square root of a number x always less than x is if you choose a number that is between 0 and 1. So it needs to be smaller than 1, but it needs to be bigger than 0. And then any of those numbers, if you take the square root of it, you will find an answer that is bigger than the number you took the square root of. That's all for this video. Remember to submit your questions on the website if you have any.